this example, we're looking at blood clotting time, and blood clotting time really varies depending on the type and the severity of the wound. So we don't want to take this information and apply it to all scenarios. But different species have different blood clotting times. And so historically, like when we were looking at the first heart transplant, at first dogs were used as the experimental animal because a large dog has a similar sized heart to a human. However, the clotting time for blood for dogs is very much faster than humans, and so it made completing the surgery really difficult. Then they switched to using a small calf, again looking at a similar size heart to that of humans, but the cow had a similar blood clotting time, and so it will allow a similar scenario for the surgery and to see if they could get the new heart installed, and they were successful with that. And now we can have this open heart surgery and transplant surgery. They weren't looking at transplanting the heart, but actually replacing the valve in the heart. And we can have that surgery now because of those experimentations. So that's a lot of history. But in this scenario, we have the clotting time that is normally distributed, and based on a specific scenario, we have a mean of 7.45 minutes, standard deviation 3.6 minutes. So normally distributed is my keyword to draw myself a bell-shaped curve. In the center of that bell-shaped curve is where I put the mean of 7.45. And I mark off 3 standard deviations, both above and below the mean. So this part of this has gotten to be pretty standard. Every single question, we do this part the same. We know that for those values that are above the mean, the positive standard deviation is where we add. So in this section, we will add 3.6. And to the left is where we subtract. And because of the standard deviation, we'll subtract 3.6. So I'm going to go through and fill in these values. If you want to pause the video and fill in the values for yourself and then turn it back on, and you can double check that your math is correct. One thing that is unusual here is that I did get a negative value when I was doing all the subtractions. So my smallest value is negative, and that's just how it worked out. No cause for alarm. I just put it in there. I know that realistic, I'm not going to have anybody fall that low on the curve because a negative blood clotting value doesn't make sense in real life. All right, so my curve is labeled, and now I want to deal with shading. So it asks me what percent of individuals have a clotting time that is less than 2 minutes. So that's the first place that I want to mark on my graph. So 2 minutes would be somewhere between -1 and -2 standard deviations. So I'm going to put it here, 2 minutes. And it says less than. So I'm going to shade to the left of this section. And then keyword here, or greater than 11. So I'm going to put 11. 11 is almost at 1, so right before that. And greater than would be above. So I'm shading this section. So I have 2 categories, and I have the or because they don't overlap. And so on the left, I shaded less than. On the right, I shaded greater than. So in order to figure this out, we're going to go to technology, and we're using this app from the Dana Center for the normal distribution. In the app, we're going to go to our second tab to find a probability. And so we start by entering the mean of 7.45. Standard deviation was 3.6. And because this is not overlapping, I'm going to do each probability separately. that means the first one I'm going to do is the lower tail, and I'm looking for value, the percent of values less than 2. So doing that one, I get 6.5% is less than 2. So right down here, 6.5%. And then as a separate one, I have the same mean, same standard deviation. I'm going to do the upper tail, and this time I'm looking for values that are greater than 11. And so the app tells me 16.2%. So let's value up here, 16.2%. So because of that word or, I want to know the people in either category, so I'm going to add those two percentages together. So 6.5 plus 16.2. And honestly, I used my calculator to do this, but I get 22.7% is less than 2. Minutes or greater than 11. Now, I want to point out one thing to you in the app that we have, because you may have been thinking about doing this. So under the type of probability, we have done lower tail, upper tail, interval, this idea of two-tail. With the two-tail, I did not use it for this problem, even though I have definitely shaded two tails, the upper tail and the lower tail. The reason why is because when I look at how that probability is set up, it's using the absolute value. And so that means that my two tails have to be equal. So if I click on the two tail, you see that it puts up 2 lines, but with the values, it doesn't work out how I would want it to work out for this problem. So here I put a value of 11, and it just shows me the 16.2% that I got. Because the way that this is set up, it's supposed to be like equally spaced, and our two tails are distinctively not equal, so that is why I did not use the two tail probability, but instead I used the upper tail, got one of the answers, used the lower tail, got the other answer, and just did them individually. So our problem with blood clotting continues, so I'm going to go to my next slide. It says draw a new well-labeled shaded picture, so I drew my new picture and labeled it exactly like before. So you may need to pause here and go through and put those labels on. Then to get the shading part, it says people who have a blood clotting time of longer than 15 minutes are at risk of hemorrhage. So I'm looking for 15 minutes on here, which would be a little above the 14.65. About here, 15 minutes. And it's saying longer than, so I want to shade above 15 as my area. So now I have both well labeled and shaded picture. And then I'm told a busy emergency room expects or averages 186 people with open wounds in a week. How many of these patients would you expect to be at risk for hemorrhage? Well, in order to figure that out, I need to know what percent is blood clotting times above 15 minutes. So pulling in my app, we have the mean, the standard deviation. In here, we do want an upper tail value. Our value is now 15 instead of 11. So I see that this would be 1.8% of people that are in this category. So that's 1.8%. But now my question asks me how many patients. So it doesn't ask me a percent, so I am going to have to do some work. We know that percents are out of 100. We know that percents represent the part over the total. And so we'll use this proportion to solve. So 1.8% would be 1.8 out of 100. The 186 people are the total people with open wounds. and we want to know how many people are at risk for hemorrhage. So I solve this by cross multiply. I take 1.8 times 186, and so that gives me 100x is equal to 334.8. And then I divide both sides by 100. So x equals 3.348. And this is people, so I will round. Looking at the tens position, I will round this to just 3 people. So of all of those who come in, just a few people are at risk for hemorrhaging. The rest, their blood will start clotting. Obviously, we want to get them help. They're in the emergency room, all of that. But we have that extra step when it asks us for how many as opposed to what percentage.